Okay, let's get started. So for today's seminar, this is our last one for the CSP seminar series over this semester. I know most students may be very busy with like all the finals, project, and all the other things. So really appreciate all the people join us in person, also through the room. So let's first give a brief introduction for our speaker today. Yeah, so Professor Yang Chen is currently an assistant professor in the Department of Statistics at UMich, and also the research assistant professor in the MIDAS, the Michigan Institution for Data Science. We host a lot of like events and also the workshops conference for the data science. And so Dr. Chen received her PhD in the 2017, and also received a bachelor degree in the mathematics and applied mathematics from the University of Science and Technology in China in the 2011. And her research field include the Bayesian modeling and computation, hidden Markov models, and the general finite mixture models, with a lot of like applications very interesting in the astronomy, the space science, and also for the large-scale imaging data, spatial temporal data analysis. So we are looking forward to hear, including both like the theoretical, mathematical, statistical perspective, and also the application, very interesting applications and all these kind of different examples. So yeah, Dr. Chen, please take away.
Thank you so much. Hello, everyone. It's my great pleasure to speak on the North Campus finally. I'm a statistician, but I have been working on solar imaging data for quite a few years. And I hope to get some of you excited about solar imaging data so that I can learn some of the signal processing techniques to be applied in the future to the statistical analysis pipelines. Because there are things that statistical models can solve, and there are also many other things that statistical model cannot really solve in these kind of problems. So today, instead of focusing more on the statistical models, I'll be focusing on the data analytic opportunities and challenges that I have identified about solar eruption forecasting problems, especially with the imaging data that I have identified over the past few years of working on this problem. And I do see a few familiar names and faces in the room and Zoom. Thanks for coming. So a brief introduction. Right now we're standing on the Earth, and we're impacted by the sun by quite a lot. And it kind of sends out a constant stream of particles and energy, which looks like this. This is a very exaggerated visualization, but it's trying to show how the space weather conditions might be impacting the Earth, which is like a tiny dot right in here towards the corner in this image. And over the past few years, I've been working on space weather monitoring. So typically, we check weather forecasting because that impacts our transportation and everyday life. We think about rain, snow, heat, and wind. And yesterday, I was kind of worried that the weather will get really, really bad. And there was a ton of warning about tornadoes, but nothing happened, which is like a pleasant surprise. So the similar thing happens in the bigger space. Space weather is trying to study the condition between the sun and the Earth, or in other words, the impact of the solar activities on the Earth itself. And we care about radio blackouts, solar radiation storms, and geomagnetic storms caused by disturbances from the sun. So this figure essentially summarizes a lot of the topics that I have been studying over the years using statistical approaches. So here is the sun, the solar surface. A lot of events are happening around here, and that's propagated to the near Earth environment. So this tiny little ball is our Earth. It's surrounded by magnetic fields. So solar eruptions means solar flares and coronal mass ejections and the solar energetic particles. Those three are very, very important solar eruptions that are impacting the Earth in different kinds of aspects. And then in terms of terrestrial impacts, we examine geomagnetic storms and geomagnetic indices in real time, and then try to make forecasting of the disturbances of the solar activities on the Earth. So essentially, there are many, many forecasting problems and also problems that are closely related to the physics of the solar activities, especially about the magnetic field in this type of problems. So interestingly, this year is identified to be the heliophysics big year. We just watched the solar eclipse, which is not a total eclipse, but good enough for people to be amazed about how the sun kind of changes and then darkens the entire afternoon and then comes back in shape. And heliophysics is the study of our star and how it interacts with everything in our solar system. And it's kind of catching our eye, not because of solar eclipse, because it's like a fun activity, but it doesn't really cause our economic or social disasters. So the things that we actually care are the kind of storms that happen in space that cause catastrophic economic and national security damages. Everything that's related to dollars, people care about them in this country or around the entire world. And it's also one of the obstacles for human exploration on Mars and other planets. For this kind of thing, a very small number of people on Earth care about it. But if we send a human to Mars when there is a major solar eruption, especially solar energetic particle event happening, that person will be just killed. So that kind of things can lead to very disastrous kind of events. So one concrete example that people always give is the Halloween solar storm in 2003. This contains a series of solar storms. X45 means that this is an extremely strong solar flare event. On Earth, it caused a 1 hour-long power outage in an entire country, and a lot of the satellite-based systems and communications got affected. And nowadays, we cannot afford to get any of those satellite-based systems to be interrupted. And aircraft has to avoid the high latitudes and polar regions, and it affected causing a lot of airport delays. And this is not, space weather is never a reason that people identify for airport delays, but it's actually one of those reasons. And then in terms of satellites and the spacecraft, it kind of disrupted a lot of those too. So in terms of what we can do about the space weather events, what we want to do is we want to monitor them in real time and be able to forecast it. And then over the years, people have designed all kinds of flying objects in the sky called satellites and observatories to actually observe what's happening near the sun. This darker one is the one that's closest to the sun so that it doesn't really get burnt. And then there are many more that's more surrounding the Earth, trying to measure the actual space weather impact on the Earth. What is the perturbation on the space, on the magnetic field on the Earth? So the major data sets that I have been analyzing over the years include this one, SDO, which is the major data source that I'm going to talk about, and then a few like this SOHO and ACE satellites. And these kind of satellites, the Stereo and Hinode, we kind of consider them too. And we also benefit from this particular satellites. So you can see that you can tell that there are still a ton of satellite data that comes in real time that I have never touched before, even after studying this subject and working on the data purely for years. There's a ton of opportunities from a data-driven perspective for space weather monitoring. And traditionally, in their field, they rely on partial differential equations or physics models to do the prediction. But we know their prediction accuracy is actually very bad because the sun is a very complicated system. And in order to predict, their lead time is very, very small. And over the past few years, especially after 2015, as I identified, with a few seminal papers published about the potential of being able to predict the solar flare events with high accuracy using purely data-driven approaches, people have been getting excited about the potential of using data-driven approaches and especially machine learning algorithms. That does not sound like a surprise, right? At the right time, that this kind of things can become revolutionary for the field. So funding agencies begin putting more attention on data-driven approaches, that's where the flood of data about papers that addresses space weather prediction problems using data-driven approaches comes into our eye. And that's around the time that we joined the competition. So in terms of space weather data analytical challenges, I'm just listing a few that we have studied in the past. So we started out with this one topic, which is called a solar flare prediction, which is a very straightforward prediction topic that if you want to get one space weather prediction problem, solar flare prediction is the one that comes into your eye. In the literature, there is already, I would say, more than 100 papers published about using all kinds of machine learning algorithms to predict the solar flare eruptions. So the things that we did is that similarly to what other people publish in literature, we studied the binary classification problem of solar flares, whether it's a strong flare versus a weak flare, which I'll talk about later. This is a converting originally very complicated data set into a pure binary classification problem to be a standard machine learning problem. And I'll talk about very soon that this is not the right way of processing and predicting solar flares on the fly. And the other thing that we tried is about solar flare intensity prediction. This is a less studied subject because people focus too much on the binary classification problem. So intensity prediction is very important for us because the intense, really intense solar flares will be impacting us much more than the less intense events. So we did get one of those models working. And then we were trying to understand the driving forces and the features of flare eruption by doing some kind of feature engineering and feature extraction, and trying to adopt the physics knowledge within this process to facilitate a better solar flare prediction model. So that's also something that I'll go through very quickly. And right now we're trying to design a probabilistic forecasting model with a quantified uncertainty because we realized over the years that however complicated model that you apply, or however appropriate models that you're trying to apply, there's an upper bound of how accurate you can predict the flares. You just cannot hit the 100% accuracy, or you cannot hit the Google image classification type of accuracy. And then with that, we need to know what is the actual uncertainty of the predicted flare class and also the predicted flare intensity so that people can make conscious choices. So a lot of the efforts are geared towards uncertainty quantification nowadays. And then in terms of other things in space weather data analytic challenges, we actually did quite a bit of work in terms of geomagnetic index prediction. So that draws our attention from the sun all the way to the earth, locally how we're getting affected. So we have worked on heterogeneous time series prediction models and the map forecasting problems with tensor and vector predictors. So those series of models are essentially trying to predict time series of vectors and time series of matrices that kind of examine the near Earth environments. On a separate thread of projects, we actually work on data assimilation and uncertainty quantification, which actually bridges the data-driven approaches, the purely data-driven approaches, and the numerical models, the partial differential equation models, by trying to bridge those two kinds of models and using Bayesian approaches to better design the numerical experiments, and then using the actual observations to better constrain the numerical solutions. So those are the spectrum of space weather data-driven approaches that I have been working on. So today I'll be focusing on the solar flare predictions, which I identify as the #1 topic that people try to address when they go into the field of space weather predictions. So a brief introduction of solar flares. Maybe you already know about solar flares, or maybe you have never heard about what is a solar flare, but essentially those are related to the sunspots. I think everyone should know about sunspots. They are just dark spots on the sun. And then the solar flare is just a sudden explosion of energy. It just imagine the sun suddenly get angry at one single small region, and then it gets some energy out into the space. Sometimes, in many of those times, those are accompanied by charged particles, and that can be very bad for the space weather environment. And the things that we care about is kind of strong solar flares, because the sun gets angry pretty frequently. It's like a child, but then it doesn't throw big tantrums all the time. So the big tantrums that's corresponding to the strong flares does not really happen a lot, but those can be very, very bad for the space weather environment. And the thing that we want to monitor in real time is actually the stronger flares. So there are a few other examples that I want to show, because as I mentioned, the 2003 example is the one that people actually always show. But in the near, closer to us, for example, in 2022, there was a very expensive solar storm where SpaceX got 40 of the Starlink satellites destroyed. So this was a super expensive solar event that happened. That's only in 2022. And actually, only a few days ago, when I was in Waterloo giving a talk on that day, there was a major solar eruption event. And I was in a taxi trying to go to the department to give my talk. And suddenly the taxi driver told me, the GPS signal is just floating around within these 2-3 buildings. I cannot really identify what's happening and where we are. And do you want to just go on your own, trying to figure out, or we ask someone for help? And it's in Canada. It's not far away from us, but it's in Canada. So I refused, and we actually asked the campus police to tell me which building I'm supposed to go. So this is during that major solar eruption event that was in March 24 to 25. During that major solar eruption event, the local magnetic field gets disturbed, so the satellite signals gets infected, and the GPS positioning got impacted. So that's my own experience of the major solar eruptions. So typically, this is what it will look like on the solar surface when a solar flare happens. It looks like this kind of loop. And then typically, the sun, majority of the regions in this sun is relatively quiet. It has activities going on, but not at that magnitude. And it's only in these localized regions, where we call active regions, that the energy gets accumulated and then finally gets erupted. So from an imaging perspective, we're getting these kind of images all the time, but the things that we're interested in are very much localized, and where they might occur will change over time. And then for each of those regions, you identify them here and then rotates around and you miss them, and we don't get to see the back of the sun. People have been debating within NASA about whether it makes sense to put things that observe the back of the sun, but it never happened because it's a lot of dollars and people have not justified why you want to do it. So we have this kind of scattered observations from the active regions when we are looking at this data.
Are those images taken from Earth or from other satellites?
From the satellites. So this is from the SDO, which I pointed out from a few slides ago. It's kind of like the satellite that's near the Earth, and that part is the sun. So let's get down to the meat of these kind of data sets. What kind of data is available and what kind of information we can learn based on those data sets. So the major data sets that we look at is, one is called the GOES data set, the other is called the SDO data sets. These kind of two data sets give you a different piece of information. So the GOES data set essentially tells you the time series of flare events, and it gives you the flare list. So essentially, it tells you what is the start time, peak time, and end time for each of those solar eruptions, and what is the corresponding flare class. And the flare classification is just by thresholding a continuum of the flare intensity, which is it's not arbitrary, but the boundary between different flare classes is not really clear. It's just a thresholding scheme. And A/B class is considered to be weak flare classes that we don't care as much. C is sort of somewhere in the middle. Sometimes a C flare event can give you something that's pretty bad, but majority of the time C plus flare events are still considered to be moderate. But then M and X class flares are considered to be extremely strong. And for the examples that I gave in the previous slides where big catastrophes happen are mostly due to strong M class flares and X class flares. So this is the I would call response variable from machine learning perspective. This is something that we want to predict and monitor in real time. And then what kind of features are available to us to actually predict those? So typically we look at magnetogram information. So this is, again, this is a disk of the sun. And then from the solar physics community, they're able to label those kind of localized regions and call them active regions. And then these kind of actual regions, sometimes they can overlap, and majority of the times they don't really overlap. And for each of those actual regions, we actually can measure 3D magnetic field information from the year 2010 and onwards. And that's the start time of the SDO instrument. But before that, from 1996 all the way to 2010, we have 2D magnetic field information. But then the thing is that the 2D magnetic field information is called the line of sight information. It doesn't contain the orthogonal direction, which is actually very, very important for assessing the solar flare intensity. So we actually, when we dig into the literature for flare predictions, if we are using 3D magnetic field information, the flare prediction performance is so much better than only using the 2D magnetic field information. That's also why I was talking that starting from the year 2014, that's where people clean up a sequence of feature spaces, like some summary statistics of those 3D magnetic field. After publishing that paper in 2014 by a Stanford group, the entire field gets super excited about using machine learning to predict the solar eruptions. Because in the past, the 2D magnetic field information, people still used the machine learning, but the field was not as excited as they were when these kind of new feature space come out. So yes.
So what's third dimension? Is that like the depth sensor information?
So sorry, what? It's essentially BX, BY, BZ. B is the magnetic field, so X direction, Y direction, and Z direction. That's the direction that's vertical, directly facing us.
I see. Is that will be relevant to like what you're showing in the picture, like how high? What's the height for
That's
the?
not directly. So you're talking about the flux rule.
Yeah. So what's the information we captured there?
You do not directly measure how high these kind of things go, but essentially you're measuring the magnetic field information that these kind of things will be disruptive about. So when this kind of flare event happens, it will disrupt the entire magnetic field. So if you think about the Earth as a magnet, this is a north, this is a south. The ideal magnetic field should just go like that. But then the Earth is not totally like that. So, but it's still kind of like magnetic field is like that. And then when there's major eruptions that happens when electrons come in, that's how you get that you make energy, right? So when electrons hit in, the magnetic field will completely change. So this is like a similar kind of scheme about the thing that you see here is just disrupting the magnetic field, but we're not exactly measuring these kind of things. This is, I think this map is a reconstructed map based on the temperature map, I think, as a different type of observation, but we actually have those information. So here I'm just mentioning the 3D magnetic field information, but shortly I'll introduce the SDO also has another set of instruments that measures the temperature map information. So that's another piece of information that we can potentially use for the predictions. And then in terms of the predictors, we already know that they kind of scatter around the solar disk and we track them in real time. They come in varying sizes of images. So the different actual region, they could be small or they could be big. So we're not handling with just a fixed size 512 by 512 all the time. It could be 512 by 512, or it could be 107 by 102. So that's another thing about the feature space. And then in terms of how many samples you have, because I'm a statistician, I care about repetitions. When you have enough repetitions, statistics can kick in, and then you can learn patterns. So when we look at how many number of flares that you get, when you look at the raw number, it looks pretty promising. It's already in terms of hundreds and thousands. And that's where central limit theorem will kick in, and everything will be in nice in shape. But if you look at only the strong flares, as I was talking about M and X class, I got a little bit disappointed because over the years, you only observe a couple of hundreds of strong flare events out of the tens of thousands of events that you observe. And in certain years, for example, 2016, the number is extremely small because the sun is not like constant. Sometimes it's happy, sometimes it's sad. It's called solar cycle. The sun goes on an 11-year solar cycle, so there's a solar maximum and there's a solar minimum. In solar minimum, the sun is just not as active. And then in terms of how they are distributed across different active regions, it's also super non-homogeneous. Some active regions can be super active throughout the entire trajectory that we observe them. They can flare with strong flares many times. Some active regions, that actually majority, only flare once or twice with a weak flare. So the strong heterogeneity across the different active regions adds another layer of trouble when we are trying to learn repeated patterns using statistical approaches for solar eruption type of events.
Question here. So why categorize it into 5 discrete categories? It feels like it should be a regression problem, not a classification problem.
That's a very good point. So this is not my classification. So in the entire literature, people have been using this to label the flare classes because it's an integer on the log 10 scale. Yeah. So they have been saying that on the log 10 scale, if it's -7 to -6 in terms of energy, the peak flux intensity, we label it in that way. And empirically, they say M and X class are the detrimental ones, but strong C class flare can be just a weak M class flare. So there's no clear boundary. So that's why I've been predicting the entire flux trajectory and putting it as a regression problem. But I'm kind of the only person who has been doing it right now in the community. But I think that's a very valid point. But again, if you're trying to put it into a regression problem, you can still cannot avoid that the tail is the important thing over there. And we're not even mentioning their connections to extreme value yet. There are several data analytic challenges that I kind of already hinted in the previous set of slides. The first one is about the strong heterogeneity. That's the 11-year solar cycle. And there was a piece of news that was in 2022 saying that the sun is not much more active than what NASA predicted. So the predicted trajectory was like this blue one, but what we're actually experiencing is like this red one. So we're actually experiencing something that's much stronger than what we expected for this particular solar cycle. And if I work hard enough over the next year, I will be able to catch up around the solar maximum, around the 2025 to 2026, to test out my model to see how the prediction models are working out in practice in a super active time range of the sun. And the other data analytic challenges, which is actually quite challenging from a statistical perspective, but may not be super challenging for you guys who work on signal processing large-scale images, is that we have multiple channels of images that looks like this at very high time cadences. So the current time cadence that we're working on is the hourly time cadence, but it actually gets down to 12-minute time cadences. And we have data for 10 years or more for these kind of images. So it's pretty large and massive scale of images. and they sort of align in some way. You can see that this is the same time, but just looking at different temperature max for these colorful ones, and this is the magnetic field. And the other thing is that with this large volume of data, the features that you extract, which is typically the kind of contrast between the black and the white lines, where we call the polarity inversion line, where the magnetic field kind of twists and accumulate energy. These kind of lines is not oriented always like this. This is after our pre-processing using PCA. So they can be like this, they can be like that, and they can be in the corner of the image, or they can be in the center of the image. So the data on the raw format is at a mess, in my opinion, for solar eruptions. And then finally, what we're actually trying to predict when you calculate the quantiles, they are the very extreme and rare events. And statistically, you don't have so many repetitions to capture their phenomenon. So in our past work, we tried to do many different things to tackle the problem from different perspectives, but have not really come up with a final ultimate model that we're so confident about for real-time forecasting yet. So we have tried feature engineering, classification, and regression problems, and trying to use those high-dimensional images and try to account for heterogeneities using mixture models. And still, we are struggling with the operational forecasting that we're trying to work on for this summer with a team of students. So in terms of feature construction, I'll go through this set of slides really quick because I think for feature construction, you probably are already very familiar with it. What we tried first is to do autoencoder to represent the high dimensional images using a low dimensional structure. And it turns out that the autoencoder, in terms of image reconstruction, is doing pretty good. But in terms of feature extraction, that might be finally useful for flare predictions, they are performing almost as good as the 16-dimensional summary statistics that the physics people constructed. So that's kind of like a good news, saying that the images are kind of good. Autoencoder is converged, but it doesn't really give us anything more exciting. And then as we talked to the space weather people, they essentially informed us that the topology of the magnetic field might contain really important information over there. So I actually used the topological data analysis and the spatial statistics information. This Ripley's case function turned out to be super useful turned out to give us a super useful feature for flare predictions. So by using physics knowledge as a combination with the statistical knowledge, we were able to calculate a bunch of spatial statistics and topological features that turned out to be very useful for flare prediction, and that can improve on top of the so-called sharp parameters. That's the 16-dimensional physics parameter that the solar physicist has collected. So that was very promising and encouraging for us to be able to extract the features that complement the original known features. This is just showing the contrast of our Ripley's case function. That's the spatial statistics features. For on average, the weak flares look like this. And the strong flare looks like that. So the distinction is actually pretty good.
How do you evaluate the performance of feature extract? Classification or...
Yeah, use it for classification. So finally, you use the skew scores for classification.
So I first train an autoencoder, then extract the feature.
Yes.
Yeah.
So it's a two-step procedure that we did. Yeah.
Autoencoders trained on images of the whole sun or on like sunspots?
Actual regions.
What's that?
The actual regions, the localized regions.
The sunspots move around. You're tracking. I mean,
Yeah, in real time. Yeah, so we're kind of having videos. And one problematic thing is that we're not using the videos in the way that we should be using. We're kind of taking, here's a flare event, and then we track what happens 24 hours before that flare happens. And if that's another flare event for the same active region, we treat it as 2 independent samples. So there are things that is not totally tackled yet in this problem, but it's a very kind of, I hate to call it engineering, but it's it's like putting it into a standard classification problem. And then when we're doing this, we're trying to convert this into a purely classification problem. We do get encouraging results in the sense that we apply that to representative active regions and see what our prediction score looks like as compared to the flares that happens. So the prediction scores actually increase all the way up to 1 around 20 to 40 hours before the first strong flare event happens. But when we track the active regions longer enough, we see problems kick in. So ideally, the prediction scores should go down all the way to 0 right after the last strong flare happens. But it's not always the case. This is the worst scenario. We're claiming it's all safe, send somebody to the universe and then that person get killed. So this is very bad. And then this is also bad. We're saying that warning is always on, well, nothing is really happening. So this is the problem, and we already know what's happening of these kind of problems. So we designed our model for flare intensity prediction, essentially trying to tackle the flare prediction problems with regression plus classification problem. Because for majority of the time, the sun is quiet, so we need to have this indicator of a quiet time, no flaring versus flaring time. And then when it actually flares, we want to predict what is the actual intensity over there. So we have 2 different kinds of loss functions over there. And we try to design our loss function based on cross entropy loss for the indicator of whether the sun is quiet or flaring versus the squared error loss for the logarithm of the intensity. So this is the model that we came up with. And it actually quite effective in terms of capturing the local maximum peak intensity in our flare eruptions. So these are 4 different active regions. For each of those, the top panel is the probability of having some flares locally in a 24-hour window. So you can see that when you have a lot of flares here, the probability score is always very high. And when you're kind of down to having no flares in this region, the probability score is kind of low. And then on the bottom, the blue curve is still our predicted local peak flux intensity. They kind of follow the dots, which are the actual observations pretty well. So this model was one of those successful models that we trained. And then we're actually very ambitious because for all of the aforementioned models, we're just using vector time series as predictors. We're just using the physics knowledge. They're extracted summary statistics, which are essentially just a mean and summations. And then we're trying to say, well, can we use the vanilla imaging data to predict the solar flares? Again, we don't have so many observations, but we can still try something because statisticians love sparse models. And we're hoping that by adding some kind of sparsity structure into a complex model, we can still run this prediction problem with a really high dimensional imaging data. So that's how we come up with this project called a scalar on tensor regression problem. Again, the input is these kind of images. We have 10 different channels that we extracted, and then the output is the flare intensity. And in a classical scalar on tensor regression problem, we define the tensor regression coefficients and put it as a simple linear regression framework. But in our case, definitely we do not want to do that because the dimensionality of the predictors increases so fast. In our case, m is equal to 10, and each of those i's is equal to hundreds. So we cannot really do this with the hundreds of strong solar flare events that we have, and in total thousands of flare events. So we did it's not a 2-step procedure, it's a joint model, but with 2 different model components. The first component is called tensor contraction. And essentially, when you have a higher dimensional matrix, if you multiply a really tall and a thin matrix to that high dimensional matrix, you get to something that's tall and thin. And when you multiply another fat and short matrix to that matrix, you get something short of that. So what we did is that we want to define a matrix two contraction operators onto the two dimensions of the images. H is the original image dimension, and W is also the original image dimension. So we do tensor operations, which is a linear operator, to compress the bigger tensor into a smaller tensor. But for the third dimension of the tensor, we don't do anything because they contain important channel information. And for this project, we were hoping to answer a question that has been confusing for the physics community for years, that does the temperature map offer extra information on top of the magnetic field information? So by keeping the channel-wise information intact in this particular model, we want to achieve interpretability of the final model. And then after the tensor contraction, which is the HX indicator operator, we put a Gaussian process model for the regression, which is pretty standard nonlinear regression model. And we fit this model using a maximum likelihood based approach. So this is just an intuitive illustration of what I just talked about. So when you have a data cube that looks kind of big, you multiply a tall matrix and a short matrix on each of those modes, and then compress it into a smaller tensor. But the last dimension gets fixed.
A and B need to learn.
Yeah, they need to be learned. So they will be learned based on the final loss function, which is how good you are fitting the flare intensity for the Gaussian process model. So you see this composite operator here. H is the A and B, denoting the A and B over here. So H depends on A and B. And then the G will connect the H to the response variable. So if you isolate just a Gaussian, in our case, it's just an IID Gaussian, then the loss function will be just the difference between those two squared.
Yeah, well, tensor contraction, is that something like low rank?
It's not like a tensor factorization or tensor decomposition. It's trying to learn, it's like a linear regression. It's trying to learn some coefficients that can compress. It's kind of related to singular value decomposition, but not totally. It's trying to extract a few, I would say, intrinsic dimensions in this tensor space, such that these intrinsic dimensions are containing information that's useful for flare prediction. Because there are so many pieces of information in the raw images, we don't care about many of them. We only care about those that are related to flare predictions. So that's why we come up with this type of model. And one important thing is that we want to extract the features that based on imaging data that have spatial continuous structures. So we want to have the A and B factors to be accounting for the fact that the input features are not just the matrices, they are images. They have spatial continuity information over there. So the loss function that we give, that is the L1 sparsity penalization that we give to the coefficient matrix, is called the total variation penalization. It actually penalizes over the gradient on the x-axis direction and y-axis direction. So this kind of sparsity solution can give us really interpretable results for the imaging type of data. So this is the final model that we have, essentially just a tensor contraction and a Gaussian process model on top of the contracted contracted tensors. And we actually, in terms of estimation, we try to integrate out the Gaussian component with the Gaussian process that reduces our computation. And then the only parameters that we need to fit are just the A and B, which are the contracting coefficients, and also the residual variance. That's a Gaussian noise term. And the way that we're fitting this is just iteratively solve for the A and B's, and also the U's are essentially the covariance, capturing the covariance matrices of the Gaussian process kernels. So we actually did a little bit of conversion analysis because again, it's a massive data set and big model. And we show that the algorithm can actually converge around a linear rate. So it's not too bad. And we were able to apply this to the final images that we get. So what I'm showing here is still a toy version of the actual flare prediction problem, because we trained the data to be 50 by 50 for all different active regions. But note that some active regions can be really large and really and 50 by 50 is making the image really blurred. And some of the actual regions are actually as small as 50 by 50. But we're keeping the 10 different channels. And also in this data here, because of our collaborators' efficiency in terms of sample collection, we can only get the really strong flares and the B-class flares images. So we don't have so many samples as I showed at the beginning of the talk. And the data is still under processing right now for the C-class flares and other flares that we care about. So we're still refining this model for now. But for this results, we're kind of just showing preliminary results after pre-processing the data by quite a bit. And then we're defining our contracted tensor size to be 3 by 3 by 10. We decide on this number just because we only have around 1,000 samples, and we're fixing this tensor dimensionality. We're not doing quite extensive model selection yet for this model. And then this is just a channel-wise average of B-class flares, you can see, and then channel-wise average for strong flares. So on the surface, you can see the B-class flares and the M-class flares should look very different from each other. So intuitively, it should not be so difficult to differentiate them. But actually, when we, this is the interpretation plot. Essentially, this is just showing what are the pixels with non-zero tensor contraction weights. We're capturing the center, which is the brightest spot, and also the boundary, which is showing how big the actual regions are in these kind of maps. So this is we're just highlighting the pixels with tensor contraction weights that are greater than a certain threshold. So it's very clear that we're capturing this so-called clarity inversion line very nicely. And the boundary pixels are just capturing how big the actual region is, or how overall the intensity for each of those images. And we were able to perform variance decomposition or analysis of variance based on this Gaussian process model, essentially telling us the variability of the observations come from multiple sources. We have channel importance, latent feature similarity, and feature map importance that's characterized by the variance kernels in our Gaussian process model. So based on this decomposition of variance, we are able to interpret which of those channels are extremely important for flare prediction. So in this case, this PIL is called polarity inversion line. This is actually a confirmation of physics knowledge because we already know that. And this is our finding that certain channels from the AI images are actually quite important, and they can be complementary to the magnetic field information over there. So we do get some really interesting insights about the different, what kind of information is contained in different channels of those images based on our analysis for this tensor contraction Gaussian process. So another project that we actually worked on, which I'm not going to talk about today, is that we actually was able to show that the flaring mechanism actually is not uniform across different active regions. You need at least 2 different functionals that links the input features to the output, which is the flare intensity in the model. So this is what we showed in a separate piece of work. And finally, what we want to do is that we want to merge all of those works together, starting from the images, and capture the heterogeneities across the flaring mechanisms in one gigantic model. Here I'm just kind of trying to wrap up the study on the flare eruptions because I feel we're running out of time. Currently, we're trying to use trying to explore what we can benefit from using extreme value theory for flare predictions. So this is one of our ongoing project. And then we're trying to use the solar cycle dependence, which is the piece of information that nobody has used yet for solar flare predictions in the real-time forecasting. And we're trying to come up with a parallelizable computational algorithm for our solar flare predictions work, because the model is quite complicated, as I showed, but the image volume is still very big. So we're kind of struggling quite a bit with that aspect. And in terms of operational forecasting, we hope to have sequential updates based on flare dependency structures, so that we have some online updating algorithms for the flare forecasting and obtain some uncertainty quantification with the flare forecasting. So I'll just conclude here that space weather give us many data analytic challenges, especially if you're working with high-dimensional imaging data. There is a lot of opportunities, but really challenging problems over there. For flare forecasting, it's one of those problems where you have very rare and strong event predictions. There are a ton of missing data over there that I didn't really have time to talk about. Missing information, strong heterogeneity is one of the most annoying features for the flare prediction problem. There's one saying in the field that whatever law that you come up with for the flare predictions, there's always one flare that breaks that law. So that's the heterogeneity problem that has been troubling us for years. And we have large data volumes of different types, which is actually a problem for many statistical models. But I hope that in the machine learning community, there are magics that can solve them, that can help with our processing. And on the side note, in terms of geomagnetic index completion and prediction problems, I worked on the sequence of video imputation and video prediction works along that direction. They also have maps, that's the global maps, at 1 degree latitude, 1 degree longitude maps. And those kind of maps are collected at the 1 minute resolution. And we have tens of years of data for these kind of maps. So again, we have very spatially sparse observations. Those maps are never complete. We have those over extended time range. So if there's any other techniques that you would recommend me to look into for these kind of map reconstruction and prediction problems, I'll be more than happy to discuss those kind of things with you too. So I'll just conclude here, and I look forward to more discussions over the future years with many of you here. Unfortunately, Qin Chu, who invited me, is not here today.
Yeah. Okay, great. Yeah, let's thank the speaker for the fantastic talk. Any questions from the audience? I see there's somebody like in the chat.
There's just yeah, it's from Alex.
Okay.
Yeah. Yeah, I know him.
Okay, great. Yeah, so I have a question. Want to ask about like the tensor-based model.
Yeah.
So I understand the intuition to add this kind of to enforce that, okay, this is actually for the space continuity and we need to make the model know that, okay, this operation is on the image. I'm just thinking, so from your opinion or experience, how important this is? So for example, when we're using like the variational encoder, the deep learning to extract the features, right? We didn't tell them, okay, the input tensor is an image or not. But it just learn something from the target from the supervision, what kind of features that we should learn from it. Yeah, so in this kind of model, how important do you think we need to add this kind of constraint or regularization term?
Regularization, right?
Yeah,
I think it's because of the sample sparsity. If we have infinite amount of samples, I think the spatial continuity will be burned automatically. But in this case, the flares that we care about is only in terms of hundreds of samples. Hundreds of events. Yeah. And then the input feature space is huge. It's in our example, it's not a big one, it's 50 by 50 by 10.
I see.
So it's really important to give L1 regularizations
I see.
to some extent to actually identify all of those model parameters.
Yeah, yeah.
You want to make sure the number of the dimensionality that you're trying to learn is much smaller than the number of observations that you get, which will guarantee a nice result that you can extrapolate into the test set. So that's the whole motivation of this L1 regularization.
That makes
And-
sense. Yeah, yeah.
Um,
I'm also,
but-
yeah,
yeah.
sorry, go ahead.
Yeah, but again, if we frame it into the regression problem and only care about the majority of the observation, that's a weak flares. We don't care about the tail, which is a strong flares. We do have enough observations to identify features.
I see. Yeah, I'm also thinking about the relevance between, this regression and also what we are using called like the weight decay, right, in the deep learning training process. So in that kind of case, it's also trying to avoid the overfitting when you are
Yeah,
training, especially on the limited training cohort. And what they are trying to regularize is the L1 or L2, like the norm on the weight parameters.
Yeah.
So I think that will be on the B and A here. So
Yeah,
what do you?
Sort of, this is our regularization term.
Yeah, right. So, but you're also considering like the gradient in some
Yeah.
direction, right? So
Yeah.
what's the intuition behind that?
Oh, the gradient regularization is just trying to make sure that the coefficient that you learn finally will be smooth. So I think it's a bad notation because I was using X for the predictors, but this X is along the X direction.
Yeah, it's understandable. So you want it to be sparse and also smooth.
Continuous, yeah.
I see. Yeah, this is very interesting.
While you have that highlighted, so why did you multiply them rather than adding them? It seems
This is directly derived from the total variation penalization term because the weight is the Kronecker product of B Kronecker A. Yeah, so this is like a byproduct for choosing the total variation, the anisotropic total variation penalization. So the original penalization is just to penalize this W, which is the coefficient on the X direction and Y direction. And then when we plug in our form for the weights, which is B Kronecker A, we can derive this. So this actually makes our computation really, really nice because they factor. So when they factor, at each of those iterations, when we fix the B, this becomes a fused lasso problem for A. And when we fix the A, it becomes a fused lasso problem for B. So we actually love this format just because computationally it gives us a really nice implementable procedure.
And what's your favorite algorithm for solving that fused lasso problem?
We just applied the original package. I think it's based on coordinate descent.
And the dimensionality of A and B, roughly, how many coordinates, in other words?
So A is just a 3x50, and B is also 3x50. It's not huge, but again, this model takes a while to run.
I mean, I'm asking because how strongly do you feel that you need exact zeros, which you get with with a soft thresholding that goes with a one norm, you get exact zeros. But if you're willing to round the corner of that, then you won't get exactly zeros, but you then have a differential constant. Not Rich, I'm not saying 2 norms squared, I'm saying, Hoover function, something like that, instead of an absolute value function. So that you have a differentiable cost function so you can apply quasi-Newton method or something that would have a better than one over.
That's right.
Have you thought about that, or do you really want a model selection here, so you really want to get rid of some of the elements?
Well, actually, in terms of interpretation, if you give me something like this or a smoothed version of this that replaces the dark spots with some light colors, I think that's also interpretable. So I think that's okay from an interpretation perspective. We're kind of doing a little bit strong in terms of pushing all the way to 0 and give you the dark spots. So I think that might be a good idea to change it to the Hoover laws that you mentioned, and then get to something that's like closer to this solution, right?
I find for a lot of my applications, I don't need exactly 0. It's good enough to have close to 0, and making a differential just makes it easy to solve. But I know it's not as sexy of an optimization problem, right? Because now it's just whatever, just Gaussian-Newton instead of fancy proximal methods or something, which I'm working on too. I have a couple of high-level questions, if you don't mind. Like, you talked about the back of the sun, so I actually don't know anything about the solar system. As we go around the sun, I assume the sun is rotating or something at a rate that's completely
Because of fixed, the sun is rotating, yeah.
Yeah, okay. So we see the back sometimes anyway, so what's the point of?
The thing is that for that actual region you're trying to track, you don't see it when it rotates away from you. So you do not see the entire lifetime of an actual region. You don't know what happens to it. And then when it comes back again, you don't know him anymore.
Yeah, because it might have changed a lot. Okay.
Yeah. Yes.
So does that mean that the probes, the other not Earth measurements are also like fixed to Earth?
No, I think the Parker actually, which is the data that we never used yet, is not fixed to the Earth. It's actually this one. I think I know this because when I was visiting Maryland, someone was actually analyzing data from there, but I don't know too much about what's happening with the Parker satellite, but it's not really used for flare predictions by the community at all for whatever reason that I'm still trying to figure out. But this is actually the satellite that goes not like fixed to the Earth. Yeah.
And where is the geometric magnet? Is that from Earth?
Oh, so SDO is actually here. This is where our data is collecting. Yeah. So this is kind of taking images from the sun snapshot by snapshot all the time. Yeah. Yeah, so this is the current 3D magnetic field that we're having, and this is the original 2D magnetic field instrument. But this, this is still a question mark for myself too. Like for whatever reason, we never used data from this. But I assume it's actually a pretty new satellite that a small group is actually working on data simulation using this particular one. Yeah.
And since for now your input tensor is HW and also channel, right? So is that for some static standpoint?
Channel is static.
Yeah, right. For some like snapshot. Do you think if you have like a sequential of images
Entire
across, it will be, yeah, it will be
That will be more ideal because in our previous study, we showed that it's actually the temporal information is quite important for the sun, but we don't have that capability right now. This algorithm is already kind of too involved to fit, yeah. But I think that would be really useful to put in there.
yeah, but definitely even higher dimension.
Yeah, it's another mode of the tensor, so it's like a 4D.
Yeah.
But then I was not a big fan of representing temporal data using the tensor because time has the direction and it's not as exchangeable. So I always want to model the time. So in a separate piece of work where I do video prediction and video imputation, I always separately model the temporal dimension because the temporal evolution should be, it's not like the temporal dimension is not just any third dimension of a map. So you want to model the evolution, especially in physics, the temporal gradient, most of the time is the most important predictor. So we want to be able to model those kind of information.
I see, like the relative temperature.
Yeah, exactly. And I was hoping to use time series type of analysis techniques for those kind of information. For example, like autoregressive type of approaches or a time-dependent stochastic process type of thing. Yeah.
You just mentioned the time dimension not exchangeable, but even the spatial dimensions, you're applying gradients because you want
No,
smoothness.
it's not extreme either. So that's why we love the total variation norm that penalizes those two dimensions. So those are all compromises that I'm making. The only thing that's extreme is the channel information. Yeah. So I think for spatial temporal data, I would not say like this final model that I'm presenting is the model that I would love the most, but it's kind of getting closer to where I want it to be, like going from the vanilla images. Ideally, what we hope to propose is that we go from the original solar disk data, the full disk data, which is 4,004, around 4,000 by 4,000.
Good luck training your PhD.
Yeah. So ideally, you want to get something that looks like that work, but right now we're just doing a lot of pre-processing using PCA to rotate the images, to align them. So we do a lot of those kind of things ahead of time, and then put them into a reasonable model to get it run. Yeah, still a lot of open problems, I think.
Yeah, very interesting. Anything else? Oh, yeah.
I have a question on the multi-class classification problem on
Yeah,
page 17.
yeah, sure.
It seems that for this, it seems that for this, we should use some kind of regression loss.
Yeah, it is. Yeah, it is. Yeah, so that's why I'm saying in the second model that I presented, I actually take the logarithm of the flare intensity and then use the O2 loss for those. But then the sign is like it's kind of quiet for majority of the time, so we need to have like a mixture model for that. With a certain probability is quiet and you predict that probability, and with a certain probability is flaring, and given that is flaring, you predict what is the actual intensity on the log scale. And whether log transformation is the right transformation to do or not, we're still exploring, because there's a lot of missing information in the recording of the flare list that I didn't really mention, because the way that they handle it is that when you have a big peak that looks like a flare, they record it, and then the local smaller ones that's smaller than those get ignored. So you can see that you kind of misclassify a lot of those weaker flare events and missing a lot of them. And there's not a way of filling them. So the raw flare intensity distribution should follow a power law distribution, but the actual flare distribution, as you can see from my table, it looks like a unit, like a unimodal type of distribution. So you're missing like an entire picture of the weaker flare events. And when you're training a model that you want to label the non-flaring times as really non-flaring, is not really correct. So that's why even after developing this model, predicting flare intensity, we do not stop there, because with that complicated missing data mechanism, who knows what kind of model we're fitting there.
They censor that data just for saving power for communication or to reduce the amount of data, like why are the smaller flares?
It's not identifiable because the flares come and they come in like, there's a starting time and the flare kind of peak like that, and there's like a long decay time. When there's locally a biggest flare happening, the local smaller ones look like noise. Yeah, so we can go back to the bottom of the data, which tracks at the minute level what is the flare intensity flux. But yeah, it's a different challenge for the field that people do not really talk so much about, because everyone is looking at the tail of the distribution. Yes.
What is I guess the behavioral relationship between the flares and spots? Are the spots less present during the active periods?
You're talking about sunspots.
Yeah.
They just happen to be sort of next to each other because they are the cooler regions. But then the flare is like, I'll not call them a hot region, but they are where the magnetic field twist and accumulate energy. Yeah. So typically when you have a lot of sunspots, there is more probability of having solar flares. So if you look at the solar cycle dependency, it's typically the sunspot activity, the sunspot number.
Okay, cool. I think we can end here. Thank you so much again for the wonderful talk. It's very interesting.
Oh, just
Yeah,
real quick,
thanks
I'm the
for-
host now. So do I just stop recording?
Yeah, we can stop recording.
Oh,
Okay.
thank you, Victor.
Okay.
Thank you.
I did not realize we're
Yeah, my laptop battery has ran out.
my students, so it's.
Very interesting topic. I'm wondering if there is any simulation or simulator that can,
Predict the flares.
no, can simulate more data to address the heterogeneity issue.
Yeah, people do like, you know,
Uh-huh.
the data augmentation technique in computer science, people actually apply those.
Okay.
To kind of rotate the images and put it as another
But
training
just to
data.
simulate some like the synthetic data.
Yeah, synthetic data generating, I don't think that exists in the literature.
Okay.
There are physics models where you can simulate
Yeah, or physics
fake
models.
solar images,
Uh-huh.
but those are bad. Those
Okay.
help
It's
with
very hard to
reality at
transfer.
all. So the physics do not align with the observations, which is the biggest problem for their field about data simulation, because everyone wants to do data simulation. And in weather forecasting, they do very well in data simulation because their physics system is so good that the observation is kind of correcting them. Yeah.
Earth weather, yeah, okay.
Yeah,
We have
but-
lots of observations, lots of training data,
Yeah,
right?
exactly. But in space weather, it's just so chaotic that so when we study the coronal mass ejection simulations, the observation look like this and the simulation look like that. They're just like missing the peak and just completely missing the entire
Yeah.
picture. So that's why I think what the funding agency was saying is that
Uh.
you can replace certain smaller modules within the space weather forecasting framework by data-driven approaches.
Okay.
So if we're able to tell you when the flare is coming, their decay phase, the simulation is very good. So they can model like how the flare even gets diminished as time goes by very well. But they do not know like when it's coming.
I see. Yeah.
I have a very engineering question. So you said 40 satellites were destroyed by that flare.
Yeah.
Did that company have a particularly bad design that was really, or were there a lot of other satellites too that were, you said 40 SpaceX or whatever, one particular brand?
Like more than 50% of their satellites were destroyed. It was like a big economic loss for the company.
Yeah, that's,
Yeah.
but not, but other satellites were fine. So there's something in their design that was really sensitive or?
I think it's a design problem. It's
Okay.
just the satellites gets destroyed. The reason why many times we don't suffer from the space weather events in nowadays daily communication, the global like GNSS satellites, is that typically you have multiple receivers. You have multiple signals that if one of them gets destroyed, you still have like backup.
Okay.
But like in terms of like power grid, sometimes it's like only rely on one of them and it's very yeah, if you have an infinite amount of money to give this all of those robust procedures, we're kind of robust to space weather impacts, but you don't have those kind of infrastructures.
So expensive.
Well, thank you. That's a terrific overview. Thank you so much.
Yeah.
Really.
Thank you. I really enjoyed the comments that you.
Yeah.
I always like to see optimization problems and think about, you know, how to make them faster.
Versions compared to the more like fancier versions.
Because my data sets are not as big as yours, but you know, I can't use the original lasso code for my problems, right? I have to think about.
I'm not saying that the original lasso code in R only had 5 iterations.
Really?
Some very small dimensional problem, right?
Anyways,
All right, thanks.
well, I'll try those ideas about.
Okay, I'm happy to chat more with you.
Thank you.
Bye-bye.
See you.
And I gotta say, I'm sorry about the attendance, you know, we just had a very, very busy faculty recruiting season.
I totally understand, yeah.
Finals.
But having a few engaged audiences out that I hope for.
Yeah, it's also pretty interactive, I think.
Yeah.
See you. Yeah. 我们最近有在做那个 satellite image，
哦
就是用